Hi everyone, welcome to this new lecture. Today we are going to basically cover a few topics, mainly related to how does Linux and Windows do process management. And by process management, how do you create a process? How do you pass parameters to a process? How does the parent deal with the process? You might have actually taken a bit of this during your past courses, but the idea is basically to refresh your minds, and this will be actually crucial for the rest of the course. And by the way, I changed the camera, so I hope that this doesn't result in worse experience. So if this camera is worse, please tell me. Anyway, so the few questions that we are going to answer today is basically how do you build an interface that enables the operating system to work with with any processes. Uh, as we said last time, we have processes that is like the applications that are running, and the operating system needs to manage them. And you need an interface to do that, and that interface is needed to create the process, to communicate with the process, and so on and so forth. And then the question that comes next is basically uh, what kind of powers do you give to the new process? Does the new process start another new process? Can they start processes? Can they talk to different I/O subsystems? Can they stop another process? Can they communicate with another process, and so on and so forth? And then these basic operations requires an interface, and that interface is basically very design dependent, so there is no silver bullet. Every operating system takes some decisions regarding this, and we are going to basically talk a bit about Windows and Linux and how they handle this. Uh, and we are not saying that there is one single correct method. There are methods that are easier to deal with. There are methods that are harder to deal with. But each one has its own merits and has its own strength. And at the end of the day, you cater for different trade-offs. So if you are running Linux on an embedded system, it's very different from if you're running Linux uh, for for a server. And in some sense, the difference comes from the environment, right? So you have different trade-offs. But the way that Linux manages this process creation, for example, is universal across these different platforms, basically, versus other operating systems which will take the trade-offs in the system as an input to how they do the process management. So uh, let's just look a bit at what the programming interface looks like. You basically have your top tier has like few of the different applications that run on your computer, and then you have a portable operating system library, you have the system call interface, you have a portable operating system kernel, and you have the architecture that lies beneath. And we are now going to talk a bit about the system call interface and the portable OS library, as these are the topmost layer that enables different processes, different users to communicate with the innermost parts of the kernel. And you need some characteristics in such an interface. To have an interface that is usable by people, then you need it to be flexible, and that basically means that you need one stable interface that allows you to use it regardless of the version of the operating system. Because that basically means that your applications that you design over here on top will run no matter no matter if you change the system. And this is something that you see in, for example, most Windows or Linux based applications, but you also see that, for example, some of the old, very old games like Prince of Persia 1 and like Double Dragon, and I mean, these are ancient games from the 80s and early 90s. You see that they do not run easily on Windows, because sometimes you need to change the whole interface if you're changing the operating system. Nevertheless, a lot of the stuff that used to run back then still runs today. So there is still some portability in the interface that has been used. So you want flexibility. You want basically to be able to go from Windows 7 to Windows 8 without risking not being able to run your MATLAB, which you paid a few thousand kroners for. And then you want it to be safe, because this is basically the interface between you and the users. You as a kernel, you're not. So this is the interface between the kernel and the users. So you want it to be safe, such that it cannot be a source of malicious activity on your computer, for example. So you want to be able to control the safety of that and make sure that it's top tier safety basically. You want it to be reliable, as one little bug in your kernel can mess up everything from your user data to your own kernel to even the hardware. You can actually break the hardware using if you do things the wrong way in the kernel. And if you are not reliable, then you also are not mostly safe. And there are different philosophies to do this. The Linux philosophy uh, is is a bit different from what is called microkernels, for example, and we'll talk about microkernels in a bit more details later. So microkernels, basically, the philosophy there is that you do less coding, you make less mistakes, and you expose less vulnerabilities in your system. So the microkernels is an idea that has very strong fan base, and it's basically that you keep as much as possible outside of your kernel, and you keep your kernel minimal. And a good example of this is an operating system that started as a toy operating system for people to play with. It's called Minix. It was actually an educational operating system for basically giving courses on Linux or on operating systems, and on some. It was actually the. It actually appeared before Linux, and it was a toy operating system for educational purposes, and it is actually a predecessor of Linux. So Minix was the start from which Linus basically began coding Linux, and he diverged and diverted from the way the Minix operating system is built, which is basically as a microkernel, to right now the current Linux philosophy, where you have a lot in the kernel. You have a few million lines of code in the kernel. So, given that you have the reliability property, it's useless to have reliability, safety, and flexibility if your operating system is non-performant. If you cannot get performance out of this, if you can hardly run one single application on your operating system, because one way to basically enforce performance, one way to enforce reliability would be to introduce a lot of, for example, cryptographic algorithms here and there, and introduce a lot of security protocols, and basically try to do optimal scheduling and try to do a lot of things that makes your system very reliable, very safe, but very non-performant. And this is something you do not want to do, because if your operating system is something that serves few million requests per second, then you want it to be able to serve all requests very fast for a web server, for example. But even for a personal computer, you want to be able to run your games together with your Skype, together with your Facebook, without really taking a toll at your performance. And these are basically major trade-offs, and how to balance these four is a question that we are going to answer, hopefully during this lecture.